You ever asked yourself what that jumble of letters and numbers is on your Bitcoin wallet address? Well, if you haven't, I'd like to ask you, and I'd like you to ask yourself the question why? Because when you would normally invest in commodities or stocks, I'm sure that you would make sure you did your research and you would understand what's going on within those companies or those commodities. Bitcoin is and shouldn't be any different. We get a lot of information on the technical side and the fundamentals of Bitcoin. But what about the blueprint? What about what makes Bitcoin unique, special, right down to the finest details? That is what we cover on this channel. What is going on with Bitcoin under the hood? This is part of our investment journey, but it's also part of preparing for the future financial system. On this channel, we cover a lot of courses, and you'll see that we can get certificates along the way, and it's all about enhancing our skills. It is a learning journey, so it is exploratory. So, for example, I'm not a programmer, but as we go through it together and as you go along with me, you will see that instead of just having a superficial understanding of the technology, you will actually get to learn and apply it yourself. So I just want to show you a gem that I found before we go into the content. Right, so as I was looking for sources to look into hexadecimals, some resources, I came across smartcontract.engineer. You can go check it out yourself. And it basically gives you everything you need to know to do smart contracts. And the amazing thing is their pricing compared to what I've seen in the market is actually quite affordable. So $30 for me as a South African is actually really, really doable for those of us probably from a lot of the BRICS nations with the dollar or with our currencies devaluing and constantly devaluing against the dollar. This is actually amazing. So you can check that out if you're interested. And let's start going into hexadecimal. So we will have about a 10-minute break every 45 minutes or so, depending on how long this stream goes on for. I know that it can get a bit much, taking in so much information at a time. So I encourage you, if you are studying along with me, to take those breaks. And I've especially curated some music. So I hope you do enjoy that. So those numbers, well, let me go here to learnpython.org. We are covering the fundamentals in Python, right, to get a foundation so that we can better understand Bitcoin. Because all of it boils down to code at the end of the day, whether we like it or not, whether you're a programmer or not. And as we were doing formatting of strings, we came across the integers in hex representation. So it's represented by the percentage and then a lowercase x, or a percentage and an uppercase hex. And as we were going along that, I was like, when I looked at the format of the numbers, I was like, yeah, no, this looks very familiar. As someone who's been in the crypto space for quite a long time, since 2014, this was like a major breakthrough. We're not learning Python just to pass the time. It is for a purpose. It is for blueprint analysis on Bitcoin. And so that has led us to this video today, where we are going to be covering hexadecimals. So I will show you what we picked up last time through ChatGPT. In Python, the percentage x, that would be in lowercase and uppercase, format specifiers are used to convert an integer, so that would be a whole number, to its hexadecimal brackets base 16 representation. The difference between percentage x is in the case of the letters used in hexadecimal representation. Percentage x, that would be lowercase, converts an integer to a hexadecimal string using lowercase letters, and then obviously vice versa for the uppercase x. So it would convert an integer to uppercase letters. It goes only up to A to F, and we will see why shortly. We will also see why it's called base 16. Hexadecimal is a base 16 number system. It uses the digits 0 to 9 to represent values 0 to 9, and the letters A to F to represent values 10 to 15. So already that gives you a hint why it's called base 16. In total, it uses up to 16 numbers. Although it says here that it goes from values 10 to 15, remember we start from 0, and for some reason, this seems to be a feature of coding and in general, where even when we dealt with indexing, we start at the value 0 and not 1. Like we would normally think, okay, we start counting from 1. That is not the case. To use percentage x in a format string, you place it within the string where you want the hexadecimal value to appear, and follow it with the percentage operator and the integer you want to convert. If you'd like to see more about how we formatted strings, then you can go through and watch the live that we did. We covered that in quite a bit of detail. So you'll see here, this is our string. Then we've used percentage x. And for that placeholder, we've got here number. This is called, if I recall correctly, it's called a loophole. And you put it in brackets, and then you've got your percent sign. So the code knows that the values after that is what it's going to convert. Remember, this is general Python syntax. These are things we need to know, especially when it comes to reading and understanding code. Then, as we went down, I asked ChatGPT, does the code for Bitcoin use integers in hexadecimal form? How, why, and to what extent? And the answer was yes. Bitcoin, and more broadly, blockchain technology, makes extensive use of hexadecimal representations for several reasons, primarily for readability, compactness, and standardization. Here's an overview of how, why, and to what extent Bitcoin uses hexadecimal integers. We will come back to this. First, I've got some information here on what exactly hexadecimals are. So I'm going to close that one. I've also got a video lined up for you guys, which will also just help to explain it. So this is the Sailor.org Academy, and on the course of Bitcoin for Developers, it does actually talk about Hex. We are on Unit 5, which is Bitcoin data. So maybe we can just read that, even if everything doesn't make sense right now. We're going to read it anyway so that we can start contextualizing everything. Bitcoin uses a variety of encoding methods, including some unique methods, checksums, and other techniques. Understanding how Bitcoin stores and transmits data will help you to understand why these methods were chosen. From hexadecimal to base 58, these various techniques help minimize data usage, ensure immutability, and prevent errors. In this unit, you'll learn the various encoding and data storage methods used in Bitcoin, the utility these methods provide, how to convert between encoding, and how these encoding methods improve security and efficiency. Upon successful completion of this unit, you will be able to explain various encoding methods used in Bitcoin, summarize the error prevention benefits provided by base 58 and address checksums, describe the data in a Bitcoin block, and convert data between hex and base 58. I'm going to switch over to our notes because there's some key points there that, like I said, are going to help us contextualize hexadecimals within the blueprints of Bitcoin. So this is my note screen. So from that description, we've identified that hexadecimals falls under the category of Bitcoin data. Which basically concerns itself with storing and transmitting of data. Storing and transmitting. I don't really like this pen that I'm using. Maybe I need to make it smaller. I think that should work. And then we were able to pick up that there's some correlation between base 58, right, which it seems like has error prevention benefits. So base 58, I think that's better. Tell me if that's easier for you guys to read. So base 58 concerns itself with error prevention. And then we have between base 58 and hex, we look at doing a conversion. So remember, what we know up until now is the percentage x functions, or not functions, I'm actually not sure what you call those, but you incorporate that into a string, right? To convert an integer. For purposes of Bitcoin, it looks like we will be working between base 58 and hex numbers or values. Now, already we know that hexadecimals work on base 16. So that would be numbers 0 to 15. Remember, we count the 0. So we can probably assume or hypothesize that base 58 works on a similar structure, so 0 to 57. But I do stand to be corrected. Let's go back to our main screen. So I'm going to go back to Hex Encoding. Hex is a data encoding format that is often used in Bitcoin and Bitcoin applications. When working with this tech, you will often find data displayed in hex format. If you're not already familiar with hex, now is the time, since you'll certainly run into it while working with Bitcoin. Well, that's exactly what we want. So if I go back to ChatGPT, I asked ChatGPT to what extent, how, and why Bitcoin uses hexadecimals. So let's see what the use cases are for hexadecimals in Bitcoin, and then we'll go into a bit more detail. Addresses. Bitcoin addresses, while usually represented in base 58 or BEC32 formats for human readability, internally involve hexadecimal data. For instance, the public key, which is part of the address generation process, is often represented in hexadecimal. So I'm going to make a note here on my notes of BEC, I don't know if I'm pronouncing it correctly, BEC32. This is why we're also consulting different resources, because I see that the Sailor Academy didn't mention that. So that's the first thing, is addresses. The second thing is transaction IDs. In other words, TX IDs. Each Bitcoin transaction is identified by a unique transaction ID, which is a hash of the transaction data. The hash is typically represented in hexadecimal. Third use case, block hashes. Similar to transaction IDs, each block in the blockchain has a unique identifier called a block hash. This hash is also represented in hexadecimal. 4. Script and smart contracts. Bitcoin's scripting language used in transactions often involves hexadecimal representations, especially when dealing with raw script data or signatures. 5. Cryptographic keys. Private keys and public keys are often displayed and stored in hexadecimal format. This is standard practice in cryptography because hexadecimal is a compact and readable way to represent binary data. Let's ask ChatGPT, what is binary data? I know that further down, ChatGPT does explain it a little bit more. Just waiting for it to load here. Why is it so slow? Okay, I think we can start reading. Binary data is a type of data that is represented and stored using the binary number system, which consists of only two possible values, 0 and 1. So you're going to see, we're going to go into, in this session, we're going to go into bits and bytes. And I think bits, if I'm not mistaken, is also its zeros and ones. Each digit in a binary number is called, okay, I hadn't read that yet. Each digit in a binary number is called a bit. Binary data is fundamental to the operation of computers and digital systems because it is the most basic form of data that electronic devices can process directly. Key points about binary data, bits and bytes. A bit is the smallest unit of binary data, representing a single 0 or 1. A byte is a group of 8 bits and can represent 256 different values, from 0 to 255. So, for example, we will cover this in more detail, but for example, if a bit can only represent two values, a 0 and a 1, and a byte is a group of 8 bits, how many values can a byte carry or represent? My understanding is that we would say, because a byte comprises 8 bits and each one of those 8 bits can have two values, the answer would be 68 times 2. Binary number system. In binary, each position represents a power of 2. Just as in the decimal system, each position represents a power of 10. For example, the binary number 1011 represents 1 times 2 to the power of 3, plus 0 times 2 to the power of 2, plus 1 times 2 to the power of 1, plus 1 times 2 to the power of 0. So if you look here, we say 1, and then you can see there's 3 spaces after 1. So that's why it's 2 to the power of 3. And then we do the same with the 0. We can see there's 2 spaces here, and so on. Then apparently the answer we get is 11 if we actually do this calculation. So it would equal 11 in decimal. There is a video that's going to explain this better, so we're going to get to that. Use in computers. All data in a computer, whether it be text, images, audio, or video, is ultimately represented as binary data. Instructions executed by a computer CPU are also in binary form. Storage and transmission. Binary data can be stored on various media, such as hard drives, SSDs, CDs, and DVDs, all of which store data in binary form. It is also transmitted over networks in binary form. File formats. Different types of files, for example, text files, image files, executable files, are all encoded in binary. The way binary data is interpreted depends on the file format and the software used to process it. Advantages. Simplicity in design and robustness against errors. Binary data is less prone to corruption compared to other forms of data representation because each bit has only two possible states. That makes sense. If you take a moment to think about that, I'm just going to repeat that statement and I want you to think about it. Binary data is less prone to corruption compared to other forms of data representation because each bit has only two possible states. Okay, I'm not going to go into the example because I don't want to confuse this too much at this stage. So we were over here. So cryptographic keys. Private keys and public keys are often displayed and stored in hexadecimal format. This is standard practice in cryptography. Keep in mind what we just learned about errors, because hexadecimal is a compact and readable way to represent binary data. Remember, can you imagine if our addresses were just zeros and ones, and because of the number of Bitcoin addresses, how many numbers you would need just to represent a unique address? I think I can understand why hexadecimals come to our advantage in that case. So now we understand what binary data is. It's basically like the foundation of computer programming. Right, so the next one is why Bitcoin uses hexadecimal. Before I do that, I'd just like to highlight the Bitcoin uses in our notes, and you can also take a screenshot if you'd like to. So I'm just going to clear this. So we are going to list the Bitcoin uses of hexadecimal. That wasn't very well centered. Okay, so we know that Bitcoin uses it for addresses, transaction IDs, block hashes, so from now on, actually, when you appreciate your wallet address, at least now we can appreciate it's basically just zeros and ones. Scripts and smart contracts. So I think I'm going to say script stroke signatures. Signatures are quite a big thing with Bitcoin, and I have a feeling we're going to go into a lot of depth about that as we do our blueprints analysis of Bitcoin. And then the last one for cryptographic key. So all of this is a simpler, or let's say a more readable way of representing binary data, which is basically just zeros and ones, and one set of these is called a bit. Just want to check something here. I feel like this might be a stupid question, but I want to ask anyway. in this statement, right? What is the difference actually between addresses and cryptographic keys? In this statement on the uses of hexadecimals in Bitcoin, can you explain to me the difference between addresses and cryptographic keys? Sorry, I think I forgot to switch keys. Sorry about that, guys. I mean, screen. Okay, so we are back on ChatGPT. I forgot to copy the statement. Not that one. Just copy that. And then go back here, copy, paste, enter. Did it do it? No. I guess there's no shortcuts. Send. In the context of Bitcoin, addresses and cryptographic keys are both essential elements, but they serve different purposes and have distinct characteristics. Here's a breakdown of the differences and their uses. Addresses. Bitcoin addresses are used to receive and send Bitcoin. They are like the public-facing email address that you share with others so they can send you Bitcoin. Representation. Bitcoin addresses are typically represented in human-readable formats, such as base 58 or big 32. Internally, these addresses involve hexadecimal data, particularly during their generation from public keys. Okay. Cryptographic keys. I didn't know this. Cryptographic keys in Bitcoin refer to the private key and the public key pair used in the Bitcoin network to sign transactions and verify signatures. I actually have a funny story to tell you guys about public and private keys. So let me just switch screens here. So I was a total like noob, right? I was at that noob stage of crypto, and we got ourselves a cold wallet. And I honestly didn't understand the difference between the public key and the private key. And we were also getting involved a lot in like DeFi. So, we were venturing out a lot, me and my husband, onto like MetaMask and Uniswap. And I think I was trying to send Bitcoin. I can't remember if it was from an exchange to my cold wallet. And can you believe it, guys? I actually, I had no clue how to do this. It was my first time. I actually sent it to the private key. So yeah, I think I was actually able to save it in the end. Like nobody took it because I think if they have your private key, then yeah, it's kind of like yours for the taking. But I've never obviously used that wallet again. But yeah, I personally think that's quite funny. See, those are the things we have to go through and deal with in this new space. Luckily, it also wasn't like a lot of money, but yeah. Let me just switch back over. Anyway, we got distracted. So now we understand the relationship. You have your address where you send and receive Bitcoin, right? And then you have your relationship, which is the cryptographic relationship between your private key and your public key pair. That's amazing. Private keys and public keys are often displayed and stored in hexadecimal format. Hexadecimal is used because it is a compact and readable way to represent the underlying binary data. Function: private key. This is a secret key that should be kept confidential. It is used to sign transactions proving ownership of the Bitcoins being spent. It is essentially a password to your Bitcoin. Okay, so don't ever use your private key to receive Bitcoin. Public key. This is derived from the private key through a cryptographic process. It is used to verify the signatures created by the private key and is part of the address generation purpose. So I'm quite happy. I didn't mean to go sideways, but I think when we get to a point where we don't understand something, and you're welcome to also say anything that you don't understand in the comments, I think it's important that we address those things. So we've summarized, we've looked at our Bitcoin uses in hexadecimal. Let's now go back to Sailor.org Academy and let's see what is actually said here. We are quite used to the base 10 decimal system. It's great for counting on your fingers, as most of us have 10 of them, but it's not always optimal for computer systems. The hexadecimal number system is a number system made up of 16 symbols. Its base 16. It turns out that hex works better than decimal for displaying binary coded values to humans. Let's take a closer look at hex and why it works well with binary data. Hexadecimal uses the numbers 0 through 9 and 6 additional symbols, the letters A through F. So we're going to use our fingers, but you'll follow through with me. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we carry on, so that's 10, then 11, A, B, C, D, E, F. So you see how we get to 60. In hexadecimal, A equals decimal 10 and F equals decimal 15. I'm going to show you a diagram because that sounds confusing, right? We know we started A here, so why? It's because we start counting from 0, okay? So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. It's because we need to start counting from 0 on both the hexadecimal and the decimal. So 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So it should only go up to 15, not 16. So my demonstration was actually wrong. So it's 0, and so 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. Okay. While trying to think in hex is rather challenging for a human who is used to thinking in decimal, it is in theory rather simple. So why is it better than decimal for computer systems? Computers, of course, use binary, a base 2 system. So remember, for each bit, it's a 0 and a 1. And that's all it can ever be. So it's two values. Hex provides a human-friendly way to represent binary values. Each hexadecimal digit represents 4 bits, half a byte, which means that a single byte can have values ranging from, oh my goodness, how many zeros is that? 8 zeros to 8 ones in binary, which can be much more compactly represented in hex as 00 to F8. Working with Bitcoin, you'll run across hex frequently. This is a basic introduction to hex, but much more info can be found in these 2 links. I want to go backwards a little bit here. Each hexadecimal digit represents 4 bits. Remember, a byte is 8 bits. One whole byte is 8 bits. So a hex is basically half a byte because it can represent 4 bits, which means that a single byte can have values ranging from, and then I just want to understand, so we got 8 zeros and 8 ones. Remember, we're working in binary, so it's only zeros and ones, which means that a single byte can have values. Each hexadecimal digit represents 4 bits. Half byte. Yeah, because remember, 1 bit is any 2 numbers, and it can be any combination. So it can be 00, it can be 01, it can be 10, or it can be 11. That is why it ends up being base 16, because here the hexadecimal is base 16. Here we've got 1, okay, 3, 4. And on the ones, we've got 1, 2, 3, 4. Remember, it's a base 2 system, a binary. Okay, so this is the range we're looking at in binary when working with hex, because a hex represents 4 bits. Okay, so I hope you understand how we get to 4. Although it's 8, each binary that can represent 2 values, and that's why we actually end up coincidentally with 16. That's why they call it, I would presume, base 16. I am going to stop here for a short break, and I will catch up with you guys in about 10 minutes. Take a coffee break, chill for a bit, and then we'll be carrying on. Back after our short break. I'm going to, before we move on to these other resources, if there's too much repetition, we won't linger on them too much. But I'd like to just make some notes on this. It might be difficult for you to see on the screen, but if I use the notepad, it might be better. Okay, there we go. Okay, so when we are looking at binary and hexadecimals, just close that. Binary and hexadecimals, excuse me, then a hexadecimal equals 4 bits. Remember, a byte equals 8 bits, which means it's therefore equal to half a byte, right? Now, we refer to it when they refer to base 16. What we identified, because remember, 1 bit can either be a 0, well, it actually is. It's a 0 and a 1, okay? So if we're just looking at zeros and ones, then 2 zeros is 1 bit. Another 2 zeros is 2 bits. Another 2 zeros is 3 bits. And another 2 zeros is 4 bits. So there's our 4 bits, right? But don't forget, we also have ones. In binary, we work with zeros and ones. So 2 ones is 1 bit. Two ones is 2 bits. Another 2 ones is 3 bits, and another 2 ones is 4 bits. So we end up with 2, 4, 6, 8, 10, 12, 14, 16. 16 in total. And then, of course, as we know by now, it's represented by 0 to 9, and then the letters A to F. Okay. I hope that explains it better. That is basically its summary of this here. So let's quickly go to Wikipedia. The hexadecimal numeral system, often shortened to hex, is a numeral system made up of 16 symbols. The standard numeral system is called decimal, which is base 10, and uses 10 symbols. So we go from 0 to 9. Hexadecimal uses the decimal numbers and 6 extra symbols. So 0 to 9, A to F. It's basically repeating what was said here on the Sailor website. Here's something that looks interesting. Computer memory is organized as an array of strings of bits called bytes. So remember, in Python, in our previous live, we went into quite a lot of depth into strings. Now it says here computer memory, and also keep in mind, sorry to just interject there, in the context of this, we're looking at Bitcoin data. So it's, as I mentioned previously, it's correlated to data and storage. So let's just go back here. Computer memory is organized as an array of strings of bits called bytes. So we have a string, right? And then we have bits, which is zeros and ones, and then we have bytes. On modern computers, each byte generally contains 8 bits, which can be conveniently be represented as 2 hexadecimal digits. Engineers and computer scientists frequently refer to each of these 4-bit values as a nibble. To avoid confusion with decimal, octal, or other numbering systems, hexadecimal numbers are sometimes written with an H after or 0x before the number. For example, 63H and 0x63 mean 63 hexadecimal. So I'm sure you've probably picked that up as well. If you're in the crypto space, I'm sure you're used to seeing that X, like that 0x, and then the numbers for your address, Well, now we know that that value actually, or that combination of letters and numbers actually represents a hexadecimal, which is basically a form of representing or number system of representing binary code, which is used and is related, excuse me, to memory and data. Just want to quickly scroll down here. I don't want to get too much distracted. I think we can go through this quickly. I will put timestamps. If there's anything you guys want to skip, you can do so. So the history. Unlike modern computers, many early computers had 6-bit bytes. Programmers of those systems typically used an alternate bit grouping system called octal. Each octal digit efficiently represents 3 bits, and a 6-bit byte can be represented as 2 octal digits. Okay, I'm actually not too concerned with octals. We've covered that already. Each digit in hexadecimal is the same as 4 digits in binary, so it's half a byte. This is interesting because I think this is where a lot of the confusion happens, where we started counting with 0 or 1. So it says here in the decimal system, which is what we're used to working with, right? Our fingers, you even saw me get confused. The first digit is the ones place. The next digit to the left is the tens place. Right, so you get 0 and then you get a 10. Then you add a 1, it becomes 10. Okay, the next is hundreds. Okay, I think we all know that. I can quickly demonstrate it. Let me just switch over. So I'll just write it on the side here. So, you get your, if we look at thousands, hundreds, tens, units, you've got your 0, and then you add another digit and it becomes 10, and you add another digit and it becomes 100, and you add another digit and it becomes 1,000. So that's what they're trying to say there. In hexadecimal, each digit can be 16 values, not 10. This means the digits have the ones place, the 16s place, and the next one is a 256's place. So 1H equals 1 decimal, 10H equals 16 decimal, and 100H equals 256 in decimal. Examples of values of hexadecimal numbers converted into binary, octal, and decimal. So let's try and understand it. So 0, we've got 0, 0, 0. We've got 1, 1, 1. Then we've got 10. 2 here. In binary, that would be 10. In the decimal, let's just see here. In hexadecimal, each digit can be 16 values, not 10. So we know it's base 16. This means the digits have the ones place, the 16's place, and the next one is the 256's place. So I get the 1, I get the 16. I don't understand. Should we ask ChatGPT? can you explain this to simple terms? Oops. I do have a video as well that I think will help clarify this. And the video will also cover how we convert binary to hexadecimal and hexadecimal to decimal. See if ChatGPT is ready. So while we wait for that, we will cover conversions. Let's just go to the other Wikipedia site. So this is a repetition of what we covered already. Let's see what ChatGPT says. In the decimal system which we use every day, each digit can be one of 10 values. Right, so we start at 0 and then we go up to 9 because that would equal to 10 because we're starting at 0, not 1. Each place value is a power of 10. The rightmost digits is the ones place, so 10 to the power of 0. So we start counting from the right. So we did that right at the beginning of this video. And then here it would be 10 to the power of 1. And then 7 to the power of 2. And 6, and so on. In the hexadecimal system, this is now used in computing. Each digit can be one of 16 values. It's very slow. I think it's the one that goes 0 to 9 and then A to F. Regenerate. Now it's going fast. They've actually given us a nice example here of the decimal system. 1 to 123 means 1 times 100 plus 2 times 10 plus 3 times 1. It's very straightforward. Hexadecimal is a number system used in computing and digital systems. It uses 16 different digits. We do know that. 0 to 9 and then A to F. This is Batman. He's going to keep coming up now. The letters A to F represent the decimal values 10 to 15. For example, 8 in hexadecimal equals 10 in decimal, and F in hexadecimal equals 15 in decimal. Each place value is a power of 16. If we look here, you see here. So if we imagine this to be our number, where we were counting from the left, it's to the power of 16. I'm curious to see something. Calculator. So remember we had our 256 where we got a little bit confused up at the top here. Where was it? We just do a search. 256. Yeah, remember we said in hexadecimal each digit can be 16 values, not 10. This means the digits have the ones place, the 16th place, and the next one is the 256th place. Because if we say 16 times 16, that's how we get 256. Okay. 1h equals 1 decimal, 10h equals 16 decimal, and 100 is 256 in decimal. So we start at 1. It's as if you're counting. Remember, we count from right, then to the left. As you go down, like here we have 100, then it becomes 256. So 100 in decimal, excuse me, is 256 because we start at 0 on both. Then it's 1. That's fine, right? Then we know it goes up to 9, but then 10 becomes A, 11 becomes B, right? And then so on. Then it goes up to 15 because it's base 16. But now what happens when you get now to 16? Then it's gone. Then it looks like we move on to 10. That becomes 16. Then 11, that becomes 17. Then 24, that becomes 36. And 100 becomes 256. So I just don't understand at this stage the logic. So I know we go up to 15 and then 16 becomes 10. Then we have, so while we went back to 10 and then 11 and then we jumped to 24, I don't really understand. But so far I am kind of connecting the dots. Each place value is a power of 16. For example, in the number 1a hexadecimal, the rightmost digit A is in the ones place. So 16 to this power 0, which is 10 in decimal. The next digit to the left, 1, is in the 16th place. Sixteen to the power 1, which is 16 in decimal. So 1a hex means 1 times 16 plus a times 1, which is 1 times 16 plus 10 times 1 equals 26 in decimal. So the way I'm understanding it, menu, new, let me just open up my notes here. I'm just going to switch over So the rightmost digit would be, it looks like we move like this. So it would be 1, then 16, and then 256. I'm not. Okay, let me go back. Place values in hexadecimal. Yeah, I'm correct. The rightmost digit is the ones place, so 16 to the power of 0. The next digit to the left is the 16th place, 16 to the power of 1. The next digit to the left is the 256th place, 16 to the power of 2. 1 equals 1 in decimal. The digits 1 is in the ones place. 1 times 1 is 1. That's interesting. 10 would be 16. So you've got the digit 1 is in the 16th place. I get that. The digit 0 is in the ones place. And obviously 0 times 1 is 0. So we would get the value 16. Then let's try 100. So 256. So this explains it nicely. Let me show you my notes again so that you can see nicely. So the number 1, right? These are just our placeholders for reference. So we would take, it's obviously it's 1, right? To the power of 1, which is 1. So in decimal, this is our value. I'm just going to put the dec. Then if we look at 10, if we break it down, we have 1 to the power of 16. We have 0 to the power of 1. 1 to the power of 16 is 16. 0 to the power of 1 will be 0. This explains it very simply. And then if we have 100, right, and we break that down, it would be 1 to the power of 256. Okay. Obviously, this 0 to the power of 16 and 0 to the power of 1 is going to give us 0. So our answer would be 256. And I just want to go back up here where it used a letter. So 1 is 16. I get that now in this 1a. Let's also write it in our notes. If we have 1 and a, we know that 1 is now to the power of 16. But what is the a? The a, the rightmost digit a is in the ones place. 16 to the power of 0, which is 10 in decimal. A is in the ones place, which is 10 in decimal. Let's ask it, why does A in this case default to 16? Why does A in this example default to 16? I'm going to switch screens again so you can see. So in this example with the I get it with the numbers, but not the letters. So here, for example, in the number 1a, 1 is 16, right? Because we have 1, 16, and then 256 in what would normally be the 100 placeholder. This is the 16 placeholder. So why does A, the rightmost digit A is in the ones place, which is 10 in decimal? Why does it default to 16? Because it's, I don't get it. Okay, anyway, let's see what ChatGPT says. Let's clarify the example with hexadecimal values to address any confusion. In hexadecimal base 16, the letters A through F represent decimal values 10 through 15. Here's the correct way to understand and calculate hexadecimal values. So we go all the way up to 9 and we go 10 to 15. Understanding 1A. When converting the hexadecimal number 1A to decimal, follow these steps. Identify the place values. Yes, so the rightmost digit A is in the ones place. The next digit is in the 16s place. Yes. The digit A in hexadecimal is equal to 10 in decimal. The digit 1 in hexadecimal is equal to 1 in decimal. Wasn't that equal to 16? Let's go back to 1A. Yeah, it's equal to 16. The digit A, yeah, for the digit A in the ones place, 10 times 16 to the power of 0 equals 10 times 1. It equals 10. For the digits in the ones in the 16s place, that's the number 1. So 1 times 16 to the power of 1 equals 1 times 16, which equals 16. Then you add the values. So the hexadecimal number 1A equals 26. The digit 1 is in the ones place. So let's see. I think a better way of understanding this we know that A, oh sweet, I don't think I added it, that was my mistake. So we get 1 to the power of 16, which is 16. And we know that A is equal to 10 on the list because we go 0 to 9, all the way up to 9, and then A becomes 10. But now it's 16, right? It is 16 to the power of 1 because it's in the ones place, correct? 10, no, 16 to the power of 0, sorry. It's not in the ones place. 16 to the power of 0, which is 1. And 10 times 1 is obviously 10. So 16 plus 10 is 26. So, oh, sorry. Let me, okay, 26. Hey, I didn't know I could do that. So let's practice it. Let's try 1B. Let's see if we understand this. So 1, that's going to equal 16 because it's 1 times, I know it's going to equal 16. Yeah, 16 to the power of 1. Remember, this is basically 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. So because it's in what we would normally call the tens, it's 16 to the power of 1. So it's going to be equal to 16. The B is 11, right? And I can quickly check that on our list. Yeah, B is 11 in decimal, and it would be 16 to the power of 0, which is 11 times 1, which equals 11. And so our answer, if we add these two up, would be 27. So let's check that, if that is correct. So is 1B hex in decimal equal to 27? Yes. Okay. I think we understand it. So, you know what it is with maths, guys? Maths takes a lot of repetition. So, if you're interested in your own time, just practice it. It's the only way you're going to get it like in your head. We're learning, we are used to a decimal system, and now we have to think about a totally different number system. But with practice, it's actually something that will come very naturally. So but it only comes naturally if you practice it and you make mistakes and you learn. What I love about maths is you can always check yourself. It's not like one of those theoretical questions. So just to finish off here, so we identified the prefix 0x means it's hex. This is getting really complicated. I think this is getting a bit advanced for us today. I'd like us to carry on. We're going to go onto this website here, learnmebitcoin.com, right? If you are interested in going further, and I might do so myself in another live stream, then you can get all of this information from sailor.org. It is the course of Bitcoin for developers, and the section is Unit 5, Bitcoin data. And then just look for the chapter covering Hex, and you'll find the 2 links in there. To carry on, just to make sure we've got the basics right, let's go through this website, and then I have a video which will also help us. It explains it quite simply so that we can understand it. The hexadecimal numbering system uses the digits 0 to 9 and the characters A to F to represent the numbers 0 to 50. You can represent numbers from 0 to 15 using just one symbol. This system is useful for representing bytes because half a byte has 16 different combinations. So you can represent a whole byte using just 2 hexadecimal symbols. That's why a lot of data you see in Bitcoin is hexadecimal. Okay, so remember I had our 8 zeros and our 8 ones, and it's telling us, and that represents half a byte, because remember a bit is 2 values. Okay, so we each aspect of that, if we took the 8 and divided by 2, it's 4. And the same with the 1s, it's 4. So it's half a byte. But ultimately together, because it's binary, it's zeros and ones, we can have 16 different combinations. And then it says here, you can represent a whole byte using just 2 hexadecimal symbols. That's why a lot of data you see in Bitcoin is hexadecimal. And you're going to see on ChatGPT further on, we talk about how Bitcoin uses why. Sorry, we've done the how. We're going to look at why Bitcoin uses hexadecimal, and that is actually one of the reasons. Note, the letters in hexadecimal can be uppercase or lowercase. It doesn't matter. So that's an important thing to take note of. Remember when we covered our session on formatting strings, we had percentage x, and that x can be lowercase x or uppercase x. And ultimately what they're saying here, it doesn't matter if it's uppercase or lowercase, it's not going to change the value in terms of converting it, I suppose, back to a decimal. Hexa equals 6. Never thought of it that way. Okay, if you think of a hexagon, it has 6 sides. Deca equals 10. So hexadecimal refers to the fact that there are 16 different characters in this numbering system. I trust by now we understand why there's 16. If you don't, then you need to go back and go over this section again. Base converter converts a number between different bases. Is this a test? Binary, decimal, hexadecimal. So according to binary, 0b is 10. According to decimal, that would be 2. And according to base 16, hexadecimal, 0x is 2. I don't understand that. Binary, decimal, hexadecimal. Oh, I think I know what this is. There we go. Number prefixes. We use prefixes to identify numbers in hexadecimal, decimal, and binary. So we know that 0x, what we see in a lot of our wallet addresses, we know that now that's hexadecimal. If we see 0D, it means it's decimal. If we see 0B, it's binary. For example, 0x100 equals 256. And that, let me just show you here. So remember, in our example, 100, we said, and in fact, I think I even understand it a bit better now, right? The zeros don't change. Okay. Whoops. Just go here. But the 1, so we have 16 to the power of 0. That's going to give us 1. But it's a 0 times 1. So it's going to be 0. And the same here, it's going to be 16 to the power of 1, which is 16, right? But 0 times 16 is 0. Now here we have 16 to the power of 3, right? Which is, sorry, to the power of 2, which is 256. And 1 times 256 is 256. I'm sorry, it keeps doing that. If there were other values here, okay, and not series, then we would add them together. Zero D 100 equals 100. So that's binary. So it looks like that's pretty straightforward. I mean, sorry, it's decimal. We know that. Okay, if you did math at school, you know that. 100 is 100. There's no like secret code or symbols or conversions or maths going on behind the scenes. And then binary 100 equals 4. Okay, we haven't looked at the binary system. I'm not going to concern ourselves with that. We have a focus on this channel, which is Bitcoin. We don't usually prefix decimal numbers with 0D unless it makes sense to do so. So if you see 100, you can assume that it's 100. So very important going forward. I'm now going to open up a new one. And let's just zoom in. So we need to know now when we are reading anything Bitcoin related, all right, and we see 0x, we're going to know, great, this is hex or hexadecimal. If we see 0D, okay, we know it's decky. But as they just indicated, you would normally just write the number as it is, unless it's absolutely necessary to specify. And then we have 0B, and that indicates that the following numbers are going to be binary. And these are all different number systems. Hexadecimal to decimal. So we have, this is our hexadecimal, 02A13B. Remember, we start counting from here. It's going to tell us how it did it. Ha. Who feels like a challenge? I do. I'm going to try it. Menu, new. Get our black paint. Okay, so our task is we have the number. It's a hexadecimal, sorry. 0 to A, 0 to A. 1, 3, B. And our task is to now convert this into a decimal. So I'm going to, okay, you can pause the video here and try it yourself. And I'm going to give it a shot. You can also just listen through with me. So I'm going to start making my notes here. So this would be 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, 16 to the power of 4, and then 16 to the power of 5. So B, probably a good idea to have a chart. B is 11. Okay. So starting with B. Remember, we do this from the right. So we have 11 plus 16 to the power of 0, which is basically 1. Is it 11? It's times, sorry, times 1. So it's 11 times 1, which equals 11. Okay. 3 is quite simply a 3. So it's going to be 3 times Is it times 16 to the power of 1? Is it? Was it plus? Anyway, yep, it's times. Okay. So 3 times 16 to the power of 1. 16 to the power of 1 is 16. So 3 times 16 equals 48. 48. Now, I believe that's a 1. It's difficult to write on here. So 1, also a number is straightforward. So it's going to be 1 times 16 to the power of 2, which is 256. And well, if you times that by 1, you're going to have 256. Now we get to A. A is 10. 10 times 16 to the power of 3. So let's work out 16 to the power of 3. So we're going to multiply 16 3 times. So 16 times 16 times 16 equals, am I right? Yeah, sorry, 16 times 16 times 16. Okay, that looks better. I was getting some weird answer. So it's 4096, right? 16 to the power of 3, 4096. And we're timesing it by 10, so we're just going to add a 0. And then 2 is just a 2. And then we have 16 to the power of 4. So now 16 to the power of 4, I take that and I times it by 16. And I times that by 2. By 2. Where's my notes? Yeah, we times it by 2. And we get 131,072. 131,072. I'm going to zoom out a little. So, 1. Okay, then the last one is 0. I think we can already conclude that that will be 0, but just for the sake of clarifying, it would be 0 times 16 to the power of 5. Whatever that answer is, if we times it by 0, we get 0. And now all we have to do is add these up. So 11 plus 48 plus 256 plus 40960 plus 131,072. And let's see what we get. 11 plus 48 plus 256 plus 40960 plus 131,072 equals 172,347. 172,347. And let us see if we are right. 172,347. I think now we can actually see how simple it is. Any number to the power of 0 is 1. Remember that. So maths tip. Okay, tip. You don't have to be able to convert hexadecimal to decimal in your head, but it's good to remember that ultimately you're just looking at numbers when you're looking at hexadecimal digits and characters. Tip. Little Endian. Most numbers stored within fields in Bitcoin data are in Little Endian, where the bytes are in reverse order. So you need to reverse the order of bytes first before converting to decimal. Most numbers stored within fields in Bitcoin data are in Little Endian. Should we ask ChatGPT why? Can you explain to me why this is the case? And just paste it. Endianness refers to the order in which bytes are arranged within a multi-byte number, such as 16 bits, oh my goodness, 32 bits, or 64-bit value, when memory is stored or transmitted over a network. Big Endian, the most significant bytes, the big end, is stored first, at the lowest memory address. For the hex value 0x, blah, 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 the bytes are stored as 12, 34, 56, 78. Fine. Little Endian. The least significant bytes, the little end, is stored first at the lowest memory address. For example, the hex value 0x, blah, 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 the bytes are stored. So that's the one that reverses it. So it starts with 1, 2, 3, 4, but then the bytes are stored as, so it was 1, 2, 3, 4, now it's 2, 1, 4, 3. I think that makes sense. It's like you're reversing it. You need to look here at the screen to kind of make sense of it. So remember, bytes are bits are 2 values. So the bytes are in reverse order. So in the example they've given us, I'll quickly switch over. So just to show you on a bigger screen, so when we are using Little Endian, it's called Little Endian. It's not what you think it is, like where the numbers are literally reversed. So for example, we have 0x and then 1, 2, 3, 4, 5, 6, 7, 8. We look at these data in groups of 2, and what will happen is it's actually recorded, right? Going backwards as not, it doesn't start at 8, we're just reversing these little bits here. So it would be 2, 1, 4, 3, 6, 5, 8, 7. No, I think I was looking at the wrong example. Ignore that. Sorry, guys. So it would be 8, 7. Let's just double check that. No, I'm right. I'm right. But where I got confused was here with the 2 digits. So So these don't change order. So it's 7, 8. It's just that we're reading it now instead of from left to right, we're reading it from right to left. And I think an easy way to remember this, right, is we're working with binary data. So always think of your numbers in twos. So then you just work backwards in twos. So 7, 8, 5, 6, 3, 4, 1, 2. Let me just double check that. 7, 8, 5, 6, 3, 4, 1, 2. That's little Endian. Now let's find out why. And I think we should take a short break. I know this is a lot of information to take in. Why little Endian? Little Endian format is commonly used in many computing systems, such as those using Intel x86 architecture, because it can be more efficient for certain operations. Okay. Little Endian in Bitcoin. In Bitcoin, many fields like transaction amounts, output indices, and block headers are stored in Little Endian formats. This means that when you look at raw Bitcoin data, you need to reverse the order of bytes before interpreting the value in decimal form. Converting Little Endian to decimal. Example, Little Endian value. Suppose you have a 4 bytes Little Endian value, 78563412. To revert it to Big Endian, which is more intuitive for reading the value, you reverse it. So remember what I said? You keep the 2 digits together. So those you don't reverse, you just reverse the order. So now the 12, which is at the back, is going to come to the front. Then the 34, then the 56, then the 78. And now we can interpret the reversed value as a hexadecimal number. And that we've already done. So I'm quite happy that we don't need to repeat that. I still don't really understand why Bitcoin does that. So let's just find out. One is historical reasons. Many systems and protocols, especially those built on Intel architectures, use Little Endian format. Bitcoin, created by Satoshi Nakamoto, follows many conventions common in computing and cryptography. Efficiency. Little Endian format can be more efficient for certain low-level operations, such as those performed by CPUs in arithmetic calculations. In summary, understanding and correctly interpreting Little Endian format is crucial when dealing with Bitcoin data to ensure accurate processing and conversion of values. Hectic. Okay, so from what I can understand, and I think this is good enough for us to know as non-programmers, right, that the data, Bitcoin data, and I think it mentions it more specifically here, the transaction amounts, output indices, and block headers are stored in Little Endian format. Okie dokie. So it means we just need to keep that in mind. Okay, so it needs to be reversed. So that's actually a very important point. Then we have code examples. Guys, let's take a 10-minute break. I feel like this is going on quite long, so we can do probably another hour. What I will do then for the next hour is I'll show you the video, which explains in a little bit more detail bits and bytes, and of course hexadecimals, just so that we can repeat that, make sure we understand it. And then I also just want to finish the discussion here on ChatGPT why Bitcoin uses hexadecimal. So we can just revise that. And then I think we'll just end off with a recap. And yeah, then I'll see you guys in 10 minutes. Sorry, I see we went a bit over there. My sincere apologies. Let's resume. We will be wrapping up now in this last bit of the video of our learning session. If you've made it this far, let's give ourselves a pat on the back. This is not easy. Please like, subscribe. I have looked up some stats and I've noticed that a lot of users or viewers on YouTube that are into crypto are male. So I would just like to take this opportunity to say, if you are married or you have a partner, like get your spouse involved, your wife, your better half. This is about, especially if you're in a marriage or a serious relationship, it's a team effort. And it's important for, I think, both parties to be involved and to be on the same page. Remember, like I said, this is about getting into Bitcoin under the hood so that we actually know what we're getting into and what we're investing in. And most importantly, we are prepared for the future financial system. You never know by having this knowledge, getting these certificates. Mark Saylor, the course gives you a certificate. The course I showed you earlier on smart contracts for $30. Actually, I don't know if that gives you a certificate, but you can actually build stuff through that course, and it's also can help you guys to be possibly job ready in this new space that is developing with Bitcoin and especially with BSV and its potential of 1 million transactions a second. Let us resume. So I said we were going to go onto this ChatGPT. So we should now have a good understanding of hexadecimals. So why does Bitcoin use hexadecimal? There are 4 main reasons here. The one is readability. So remember we picked up that in terms of representing numbers, what would now end up being a huge sum of numbers can be basically reduced to like 2 digits. So hexadecimal representation is more human readable than binary. It is easier to read and write than long binary strings, while still being closer to the underlying binary data than decimal. 2 is compactness. Hexadecimal representation is more compact than binary. It uses 4 bits per digit, remember that's half a byte, which makes it concise and less prone to error when manually inspected or entered. Standardization. Hexadecimal is widely used in computing and cryptography. This makes it a standard way to represent data, ensuring consistency and compatibility across different systems and platforms. That makes sense. And then 4, efficient debugging and development. Developers and cryptographers are accustomed to working with hexadecimal. This makes debugging, development, and verification processes more efficient. And I think that goes in line with the third aspect that I just mentioned of standardization, because actually, if you think about it, it's so close to binary, which is basic computing language. It makes sense that it is consistent and compatible across different platforms. So actually, we're focusing on Python, but it can apply to Java, I presume. It can apply to Solidity. So, yeah. Right, so the rest is we've already looked at the extent of hexadecimal use. So your private keys, your public keys, your transaction hashes, your block hashes. And you may also add addresses. I'm going to share with you guys a video which explains bits and bytes in a bit more detail. I'm just going to switch screens here. So let's just switch over. Apologies for that delay. So this is our video that we'll be checking out. It is under Creative Commons. It's from the Smart Contract Programmer. So they are the ones that actually have this course that I was showing you on Solidity and other aspects of Web3, as you could call it. And it explains what are bits, bytes, and hex.
Zero x 0400 is equal to 1024, which is the number of subscribers that this channel has surpassed. So in this video, I'm going to explain how to convert hexadecimal number, the number that you see on the left, to human readable number, the number that you see on the right. And in the process, I'll explain how bytes 32 and unt256, the two basic data types in smart contract language like Solidity and Viper, are equal. In other words, how to convert between bytes 32 and unt256. So first, let's understand bits, bytes, and hex. One bit is equal to 0 or a 1. So I'm going to ask you a simple question. How many numbers can one bit represent? Well, since a bit is either equal to a 0 or a 1, this means that a single bit can represent two numbers. One byte is equal to 8 bits. So you can think about it as a sequence of zeros and ones where the length of the sequence is equal to 8. For example, a sequence of 8 zeros is 1 byte. Another example is a sequence of ones and zeros. And another example is all ones. These all represent a number that is 1 byte. So now I'm going to ask you the question, how many numbers can 1 byte represent? This isn't a trivial question. So let's take a step back and try to answer simpler questions. And then we'll come back to answer this question. So let's try to answer the question, how many numbers can 2 bits represent? Well, this is easy. We can just count them. 0, 0, 0, 1, 1, 0, and 1, 1. That's 4 numbers. How about 3 bits? How many numbers can it represent? This time, instead of listing out all the possible 3 bits and then counting them, let's be a little bit clever here. We know that all 3 bits is either going to start with a 0 followed by 2 bits of zeros and ones, or it's going to start with a 1 followed by 2 bits of zeros and ones. And how many ways can we have a 0 followed by 2 bits of zeros and ones? Well, this is equal to the number of 2-bit representations. And for the same reasoning, the number of possible ways that we can have a 1 followed by 2 bits of zeros and ones is equal to the number of 2-bit representations. So in total, we have 2 times the number of 2-bit representations. The number of 2-bit representations, we know that it is equal to 4. So this is equal to 2 times 4, which is equal to 8. We can apply the same reasoning to calculate the number of 4-bit representations. A 4-bit sequence starts with a 0, followed by 3 ones and zeros, or it's going to start with a 1, followed by 3 ones and zeros. In both cases, the number of possible ways that we can arrange zeros and ones is equal to the number of 2-bit representation. We add the two cases up, and we found out earlier that the number of 3-bit representation is equal to 8. So the total is equal to 2 times 8, which is equal to 16. So let's summarize what we found so far. We found out that a single bit can represent 2 to the power of 1, which is equal to 2 numbers. 2 bits can represent 2 to the power of 2, which is equal to 4 numbers. 3 bits can represent 2 to the power of 3, which is equal to 8 numbers. And 4 bits can represent 2 to the power of 4, which is equal to 16 numbers. Notice that every time we increase the bit by 1, we double the number that it can represent. Also notice that the number representation is equal to 2 raised to the power of that bit. I hope you see the pattern here that n bits can represent 2 raised to the power of n numbers. We can now answer our original question of how many numbers can 1 byte represent. We know that 1 byte is equal to 8 bits. So this means that 1 byte can represent 2 raised to the power of 8 numbers, which is equal to 256. So for example, a sequence of 1 byte can represent any number between 0 and 255. Now I want to show you how to convert a sequence of 1 byte into a decimal value, a number that we can easily understand. So here we have a sequence of ones and zeros. We start from the leftmost value, which is equal to 1. Counting from the right and starting from the 0, this will be the 7th number. We take the power of that position. So in this case, it will be 2 to the 7th. The 6th position is equal to 0, so we don't add anything. Same with the 5th position. The 4th position is equal to 1, so we add 2 to the power of 4. Likewise, for the 3rd position, we add 2 to the power of 3. The 2nd position is equal to 1, so we add 2 to the power of 2. The 1st position is equal to 0, so we don't add anything. The 0th position is equal to 1, so we add 2 raised to the power of 0. We take the sum of this, and this is equal to 157. This was an example of how to convert binary representation into decimal values. Keep this in mind as we talk about hexadecimal values. The way we convert hexadecimal representation will be similar to how we converted binary into decimal values.
So I'm just pausing the video just to mention we had covered, we looked at decimal number system and we looked at the hexadecimal number system. We didn't look into binary, converting binary numbers to decimals. So this video has just explained exactly how we do that by using 2, which represents binary, 0 and 1, and then the applicable power. So that's how we would, in short, convert a binary to a decimal number.
So decimal are numbers that are written in combinations of 0 to 9 and 8 to F. 0 to 9 in hexadecimal is equal to 0 to 9 in decimal values. However, 10 will be equal to A, 11 will be equal to B, 12 will be C, 13 will be D, 14 will be E, and 15 will be F. So for example, if we have a hexadecimal value 3EA, here we prefix it with a 0x, just to be clear that this value.
So here, if you guys want, you can pause the video and try and do this example yourself.
Hexadecimal value. This will be equal to 3 times 16 raised to the power of 2. The 2 comes from the fact that the 3 is in the 2nd position, starting from the right and counting from 0. Next, you add 14 times 16 raised to the power of 1. 14 comes from the fact that E is equal to 14. And we raise 16 to the power 1 since E is in the 1st position. Finally, we add 10 times 16 raised to the power 0. Again, this is because A maps to 10, and we raise 16 to the power of 0 since A is in the 0th position. This will be equal to 1002. So now I want to show you that a single character of hex can be represented in 4 bits. We know that a single character of hex, so from 0 to 9 and A to F, is equal to a number between 0 and 15. That's 16 numbers, or 2 raised to the power 4 numbers. Earlier we saw that 2 raised to the power 4 numbers can be represented in 4 bits. So for example, if you have a hex value of C, A is equal to 10, B is equal to 11, so C is equal to 12. We can rewrite this as 8 plus 4, which is equal to 2 to the 3 plus 2 to the 2. And in binary, this will be equal to 1100. So now I'm going to show you how bits, bytes, and hex all relate together. 1 byte is equal to 8 bits, and 8 bits is equal to 2 hex. Let's see how. We know that 1 byte is equal to 8 bits. Rewriting 8 bits, it is equal to 2 times 4 bits. Earlier, we established that a single hex can be represented in 4 bits. So here, 2 times 4 bits can be represented in 2 hex. Let's see how to convert this into hexadecimal value. The 7th position is a 1, so we add 2 raised to the power of 7. Likewise for the 6th position, and the 5th, and the 3rd, and the 0th position. Anything greater than the 4th position, we can factor out 2 raised to the power of 4. And we write this equation in base 16. So 2 raised to the power of 4 is equal to 16 raised to the power of 1, and 1 is equal to 16 raised to the power of 0. We evaluate the expressions inside the parentheses, and it gives us 14 and 9. In hexadecimal notation, 14 is equal to E, and 9 is equal to 9. Since we're in base 16 now, we can just simply write E and F. So this gives us 0xEF. And that was an example that a sequence of 1 byte can be represented into hexadecimal characters. So finally, we can convert the hexadecimal value 0x0400 and see that it is equal to 1024. The first value in position 3, counting from the right, is equal to 0. So this does not add anything. The value in second position is equal to 4, so we multiplied 4 by 16 raised to the power of 2. The first position is a 0, and the 0th position is also a 0. So we had 0x00 is equal to 4 times 16 raised to the power of 2, and this is equal to 1024. Lastly, I'm going to show how the two data types, bytes 32 and uint256, relate to each other.
Okay. So we won't resume further as we haven't looked into bytes 32 or uint256. You'll also see there that he did binary to hex and vice versa, which is not something we covered in today's learning session. However, I do feel it has gone on for quite a bit. We will therefore carry on. I think 2 sessions should be enough to cover hexadecimals. We will resume though. There are some code examples which we will do tomorrow, and then you can see we're nearly done. And then I would like to perhaps, if you guys are interested, if it's not too complex, we can look at converting binary to hex and vice versa. And I think that should, that should meet our requirements for understanding hexadecimal and how it applies to Bitcoin, and even computing in general, how important it is. Once again, if you liked the video and you found it useful and helpful, please do subscribe. Thank you so much for watching and for learning with me. I really enjoyed it and I'm looking forward to carrying on with this. I'll see you guys. Have a great evening or day wherever you are. Thank you.